Hi, everyone. Welcome to today's webinar. We'll just give everyone about a minute to join, and then we'll start the webinar shortly. Okay, I think we can get started. Hi, everyone, and welcome to today's webinar on understanding and using the latest climate data to build resilience in the transportation sector. My name is Laura Zimmerman, and I will be your moderator for today's webinar. I am a policy analyst on the climate change adaptation team at Transport Canada. First, I would like to acknowledge that I'm speaking to you today from the traditional unceded territory of the Anishinaabe Nation. I invite you all to introduce yourselves in the chat if you would like and include your own land acknowledgement. I'm just going to go over a bit of housekeeping before we get to today's webinar. Suzanne Sealing from the Climate Risk Institute is your technical support person for the webinar today and will be available during the webinar if you run into any audio or technical issues. If you need assistance, you can click on the chat box and find her name in the drop-down menu of participants, or you can send a message to hosts and panelists. There will be a dedicated Q&A session at the end of the webinar, but please feel free to type out your questions during the presentation into the Q&A box. The chat box is also available if you would like to submit any comments. We will be recording today's webinar and sending out a link to everyone who is registered. The webinar today will be held in English, but you can find a link to the slides in both English and French in the chat box. So now I'd like to introduce our speaker for today's webinar, Ryan Smith. Ryan is a climatologist and climate service specialist with the Canadian Centre for Climate Services, the CCCS, a division of Environment and Climate Change Canada. Ryan works in the outreach and engagement team and contributes to the development of the CCCS's online data services, including ClimateData.ca. Ryan has been working in the climate services space for the past 15 years and joins us today from his home office in Winnipeg, Manitoba. So on behalf of everyone joining us, I'd like to extend a warm welcome to Ryan for presenting the webinar today. Over to you, Ryan.
Cool. Thanks, Laura. I'll just go ahead and share my screen here while this is loading up. All right, did that work?
Yes, we can see that.
Okay, wonderful. Cool. Well, thanks, everyone. Thanks for taking an hour out of your day to geek out on some climate data stuff. It is my pleasure to be here on behalf of the CCCS, the Canadian Centre for Climate Services. As Laura mentioned, I'm a part of the outreach and engagement team here at CCCS. And one of my specific core mandates is to make sure I'm reaching out to and engaging with the transportation sector. So this for me is a great opportunity, I hope, not only to deliver some content to you, but also to hear from you, to hear how we can work together, how we can partner, and I'll have more about that at the end of my presentation. So without further ado, we've got lots to get through today. I think we'll take roughly an hour, we'll see. Let's get into it. Okay, so I am here on behalf of the Canadian Centre for Climate Services, and that term, climate services, is still a bit of a new name, and it's a little bit of perhaps a confusing name if you've never heard that before. So what is a climate service? Well, The closest analogy, I think, is a weather service. And we all use weather services likely multiple times per day. Every time we check the temperature outside or the weather, we're using a weather service. And in order to have accurate, timely, well, I don't know if accurate's the right word. I'm not on the Meteorological Service of Canada team, so maybe I'm allowed to say that. But in order to have forecasts, you have to, of course, take raw meteorological data, station data. You have to be able to do some QA and QC on that data, identify erroneous values. Those values have to be fed into a forecast model. So that model has to be developed, it has to be vetted, it has to be improved over time. Those models are run multiple times. Forecasts are developed. Various forecasting products for marine and aviation, civilian, different uses. And eventually that ends up on your smartphone or on your computer as a weather forecast. It's a huge amount of infrastructure and a huge service that is provided for free to all Canadians. So in the same vein, the Canadian Centre for Climate Services is dedicated to doing the same thing, but for climate data. We take the raw climate data, the stuff that's coming out of global climate models, and trying to turn that into a product that is a little bit more useful for application at the end of the line. So that's our goal, and really, as stipulated here, our goal is to provide Canadians with information and support to consider climate change in their decision-making. And I really welcome folks to get in contact with us, and provided that contact information up on the screen, and I'll do that as well at the very end of the presentation. So we here at CCCS provide a number of different climate services. It ranges from producing new data sets. We've got some of that in today's presentation. Providing one-on-one support through our climate service support desk. I like to refer to this as the Dial a Climatologist service. So people can phone us or they can email us. Typically it's email these days, but we still get a few phone calls. And you can get that kind of one-on-one support for how do you find the information you're looking for and how do you use it in your application. Things like what we're doing today, which is an outreach presentation. We do quite a few of those. Various engagement sessions and workshops where we work with people and invite them to tell us what kind of information they need so that we can tailor our services to better fulfill that need. And lots of other stuff. Okay, so with that out of the way, we have a jammed outline here for today's presentation. There's kind of 4 chapters. First, I'm going to introduce the CMIP6 climate model projections that have very recently been launched on ClimateData.ca. So we're going to get into all the details. What is CMIP6? What are these SSP scenarios? Those are the new scenarios in the CMIP6 climate model data set. And importantly, how do I find and how do I use these data? Okay, I'll have a few live demos as well for this part of the presentation. Next, we're going to turn our attention to global warming levels. And this is increasingly how climate data providers around the world are providing their data. They're choosing to not use scenarios, but instead use global warming levels. So we're going to look at the benefits of using global warming levels in when we look at climate model data, and specifically how these can be used to understand local changes and impacts. Okay. That will feed right into a conversation about a brand new tool that was just publicly launched in February of this year called the Design Value Explorer. So we'll take a live demo of that new tool and we'll poke around. And I think that there's lots of really interesting applications to think about here. And finally, we'll do a little what's coming next section here, because we have a lot of really cool new things coming down the pipeline this year. All right, so CMIP6 data. If you want the Coles notes, the one slide that says it all, I suppose this is it. We now have new CMIP6 climate model data on ClimateData.ca. It's the default data set. As with the screenshot here, you can always toggle, though, to CMIP5 if you still want to see the previous generation of data. This new data set uses new scenarios called SSPs, Shared Socio-economic Pathways. This replaces the older RCPs, or representative concentration pathways, that you would have seen previously. This new data set contains 26 climate models, global climate model data that has been statistically downscaled to a 6 by 10 kilometer resolution at the daily time step scale. So that's a very fine scale. It allows us to go to a pretty, to zoom in and understand quite local changes, which is very powerful. And like before, the CMIP6 data that we have on ClimateData.ca is temperature and precipitation. And so you will see temperature and precipitation-based indices like number of days above 35 degrees Celsius, or number of dry spells, or length of dry spells, that sort of thing. So we'll get into all of this over the next few minutes. But like I said, this is the sort of one slide that says it all. Okay, so just taking a little bit of a step back, because you may have wondered, well, what exactly is CMIP and what's CMIP6 exactly? So CMIP stands for the Coupled Model Intercomparison Project. And this is a project that is run by the United Nations World Climate Research Program. And as it says here on the screen, the goal of this program is to help bridge science and policy. You see, if the climate modelers of the world were to just go and do their own independent research and develop climate models as in the ways they want, then likely those climate models will not be comparable. They might use different time steps. They might choose to focus only on atmospheric interactions versus biogeochemical, long-term ocean processes and that sort of thing. They might have very different ways of representing future scenarios. And so it's important that, maintaining, of course, the independence of these modeling institutions, it's important to have a core set of rules that all these organizations adhere to so that their modeling results can be compared to one another. And so if you're interested in learning more about CMIP and what its role is and how it works, then I encourage you to click on this link. By the way, as I think mentioned, you will have access to all of the presentation files in both English and French after the presentation. So you'll be able to find this, click on the link, and there's even a wonderful little short YouTube video you can watch if you want to learn more. So why do we need CMIP6? Well, I sort of already alluded to this, but it really comes down to the fact that we can't model everything. Climate models are incredibly computationally expensive to run. In fact, they use the world's most powerful computers, and they take, a long time to run. So you can't do, an infinite number of scenarios or an infinite number of experiments. You have to figure out what are the core set of experiments and scenarios that we're going to focus on. And so really, when it comes to things like I've already mentioned, the temporal and spatial resolution of the data, future greenhouse gas concentrations, long-term feedback processes, how we deal with things like microphysics, cloud particle interactions, and that sort of thing, then there is a need for some standardization because we just can't model it all. So CMIP6 data is produced and it's made publicly available for anyone who wants it. And one of the chief users of the CMIP6 data is the IPCC. It's a bit of a misnomer out there that the IPCC does climate modeling. It's not true. The IPCC uses climate models to develop its various reports that it puts out. These are called the synthesis reports, and they deal with things like impacts, vulnerability, and adaptation. And so the sixth assessment report, or AR6, was launched in 2022 and used the CMIP6 data there. Okay, so as mentioned, one of the things that needs to be standardized between climate modeling experiments is the future greenhouse gas pathways, or the scenarios that these climate models run. So, if we look at, for example, this little graph, we've got the historical temperature of Earth, and then at a certain point, climate models take over and they fan out into the future, representing all the different pathways that humanity could take. We could have some sort of high carbon pathway, SSP5, where large global temperatures are reached by the end of the century. Or we might take a path which sees the temperature of Earth peak and then begin to decline and stabilize near the end of the century, which is described by SSP1, and then everything in between. These scenarios are called, as I mentioned before, SSPs, or Shared Socio-economic Pathways, and they replace the RCPs, although I think replace is perhaps the wrong word to use. They are a bit of an enhancement of the RCPs, the representative concentration pathways that you may have seen featured on ClimateData.ca or in previous assessment reports from the IPCC. Okay. And they are a range of features that depend on greenhouse gas emissions, land use changes, and all sorts of other things that can go on to affect the global climate. Okay, so these possible development pathways have to make some interesting assumptions about the future. Chief among them are, okay, well, what will the population of the planet be over the next 100 years? Right? And so that in itself is a huge research undertaking, which requires complex models unto themselves. Similarly, education. Education is a huge factor in determining future greenhouse gas emissions, as nations with higher education levels tend to produce more greenhouse gases, right? It's a bit of a maybe backwards from the way we would think it is, but it's true, at least on a per capita level. Okay. Same thing with energy use and the type of energy that we're using. Is it coal? Is it nuclear? Is it hydro? And everything in between, right? And so all of these things have to be considered when we try to think about, well, what will the future be like? Okay. And so just showing here is a graph demonstrating one pathway for determining the future population of the Earth, which presently is projected to reach around 11 billion people by the year 2100. So there's lots of work that has to go into understanding all of these changes, and furthermore, understanding how those changes relate to greenhouse gas emissions, which really, at the end of the day, that's the most important thing, right? And so those are models that get fed into other models, which in turn get fed into climate models. These SSPs, by the way, are, I think, really, really interesting. And I think it's worth taking just a few minutes here to dive into the various narratives that describe these scenarios. So there are actually 5 SSP scenarios. Now, if I just back up for 1 second here, on this graph, we just showed 3, the blue, the green, and the red, but there's actually 5 in total. However, not all climate models run all of the scenarios. These 3, the blue, the green, and the red, are the 3 most commonly run scenarios. So they tend to be the ones you see most often, but just keep in mind that there are more. There's 5. So let's just take a minute to sort of understand the underlying narratives that drive these SSP scenarios, because like I said, I think it's a really interesting story. So if we start with SSP1 in the bottom left here in the blue, this scenario, as you can probably already tell from the icons, is one that is described by sustainable development. So policy is focused on sustainable development. There's effective global cooperation. We see reduced inequality between and within countries. Okay, so in other words, it's not the continuing development where the rich get richer and the poor get poorer, but rather a decrease in that inequality over time. There's lower overall consumption and low population growth. So this contrasts quite a bit from SSP 5, which is the fossil fuel development pathway. just a really interesting pathway when you start looking at it, because if you look at the list of descriptors for this narrative, it's not exactly a bad scenario. I mean, it is bad from a global warming and greenhouse gas point of view, but from a lot of other points of view, it's got a lot of positives. So for example, it still has reduced inequality as one of the driving narratives for this scenario, and effective international cooperation. We just continue to see the high consumption lifestyle that presently dominates many nations of the world, and a policy that is increasingly focused on allowing the free markets, capitalism, to reign supreme. So it's a very interesting scenario, and it's the scenario that does result in the highest climate change values by the end of this century. So just quickly, some of the other ones in orange here, we have SSP3, which is a regional rivalry scenario. It's a scenario described by increasing barriers to trade and cooperation, war, and other sorts of conflict that prevents the type of international cooperation that is deemed necessary to solve the climate crisis. In purple, we have a scenario that sees an increase in inequality between and within nations. And finally, SSP2, hidden in the middle of the circle here, is the middle of the road scenario, which is sort of our described as our present day policies, what we're currently doing and what we're currently tracking toward. If you're curious to learn more about these SSPs, I've got a link here to a little article which includes this graphic, and I think it's a really interesting thing to dive into. So let's just remind ourselves, why do we need these scenarios in the first place? Okay, or in other words, why can't we just forecast global warming? Okay, so by that I mean, why don't we just take the inertia that we have in the climate system right now and look forward? Where is that going to take us 20, 30, 40, 50 years from now in the future? Okay, well, of course, the biggest factor here is us, it's humanity, and it's the fact that we don't really know what it is humans are going to do in the future. Any one of these scenarios is likely to occur from at least in some degree. So it's hard to really say that one of these is the most likely outcome. Okay, and so we typically say that climate models, they're not crystal balls. They can't tell us what the climate is going to be like in the future unless we feed it some assumptions about what humanity is going to do to the climate in the future. Okay, so we kind of think of this like you're going to, go to the bank and set up some long-term investments, and the bank is going to, show you some graphs with various projections based on, well, if the global markets do this, your investment might improve or it might go down over time. This is the sort of long term. We think 90% you're going to be safe with this sort of decision. It's the same idea with the climate. As you can tell, I'm not really into banking investments. I don't really know what I'm talking about when it comes to that. That may have come across as quite obvious. I think it's similar to banking investments. You can be the judge. Okay, so enough about that sort of background stuff. CMIP6 data, it is now up and running on ClimateData.ca. Okay, so what we're going to do now here is just go for a little live demo. So I'm going to switch over to my internet browser here. Okay, so this is ClimateData.ca. And if you haven't been here before, this is a really powerful way to view and extract and download climate data. As mentioned, the CMIP6 data is the new default, but you can also always toggle to CMIP5 up here in the corner. Okay. On the bottom of the map here is the time period slider, so I can go ahead and move this slider to any point here between 1950 and 2100. I can zoom in on the map. It's running a bit slow just with the screen sharing and whatnot. And I can click anywhere on that map to bring up a time series plot showing how this particular variable that I'm looking at, in this case, it's the hottest day of the year, is projected to evolve over time under various emission scenarios. So here we can see in red, SSP 5, the high carbon scenario, SSP 2, the middle of the road, follow current policies scenario, and SSP 1, the sustainable development scenario that we've previously talked about. And you can see how these change over time up to the year 2100. There are a number of different scenarios that, there's a number of different variables that you can browse on ClimateData.ca, various temperature-based values like days with the maximum temperature above 30 degrees Celsius, for example. If I zoom out to the national scale again, oh, yeah, sorry, it is running a bit slow. It's a lot faster when you're doing it and not sharing your screen. I can also flip this switch in the top corner, which shows me the change value between this time period, 1971 to 2100, and the baseline, 1986 to 2005. And again, I can zoom in and look at how these values are expected to change for my location across the country. So in this case here, it is suggesting that under this scenario for this time period, there would be an increase of roughly 50 days per year where the maximum temperature reaches or exceeds rather 30 degrees Celsius. Okay, so the number of different temperature-based variables here. There's also precipitation-based values. So for example, here's the number of days per year with precipitation greater than 20 millimeters per day. Okay, so not much change in this part of, looks like I'm in northern Saskatchewan for this particular variable. There's things like the number of periods with more than 5 consecutive dry days. We can look at total precipitation and how that's expected to change not only for the year, but various months. So if we want to focus in on a specific month of the year. And we can always change the scenario too for what's being mapped. So lots of really cool options to explore, visualize, and download these data. Let's go back to the PowerPoint slide. One of the really powerful things about having CMIP6 data on ClimateData.ca is that, as I mentioned right at the very beginning, these data have been downscaled from their native resolution, which started out somewhere in the neighborhood of 100 plus kilometers by 100 plus kilometers, down to the local scale of about 6 by 10 kilometers in spatial resolution. This is done by performing a statistical downscaling technique that's known as BCCAQ version 2, which is, it's a complicated name and it's a complicated process and one that I won't profess to understand fully, but we have documentation that can go through all the technical details for those who want it. But essentially, this is a way of taking all of this incredible data that comes out of the CMIP6 project, 26 climate models, 1950 to 2100, and taking that data and fine-tuning it down so that we can look at the local scale changes. It's an enormously powerful way of analyzing these data, and it's what makes ClimateData.ca so special compared to a number of other websites out there. Now, one of the questions that's listed here is statistical versus dynamical. So just very quickly here, again, the process that takes the raw climate model data and distills it down to that 10-kilometer resolution uses a statistical process, okay? And that is one way to do it. You could also use dynamical downscaling, also known as regional climate modeling. And that's a process that can have many benefits over statistical downscaling. So later in this presentation, we're going to look at a product that uses dynamical or regional climate model downscaling. and we'll be able to compare and contrast a little bit how the different methods work. But for now, just accept that this is a statistical downscale product. Okay, and so as we already talked about, this is what you get when you click on ClimateData.ca, when you zoom in onto the map and look at a time series plot. One of the other really interesting features of ClimateData.ca is the Analyze page. So that's at ClimateData.ca/analyze. And actually, I'm going to take us through another live demo of this as well. So I've got the Analyze page all loaded up here. What this application allows you to do, and we'll sort of walk through it quickly here together. So we, first of all, we're going to choose a data set. So we can choose CMIP 6 or a CMIP 5. Then we get to choose a location on the map. There's a couple of predefined locations, or we can just use the grid that we were using before. So let's do that. Let's zoom into the map. Choose a place here in central Manitoba, click a location. And then I can go ahead and customize any one of these variables listed here. So for example, heat waves. Let's click on that. Now we get a little definition of a heat wave that we get to customize. So this analysis returns the number of days in a heat wave defined as when the temperature is greater than or equal to, let's say, 33 degrees. Sorry, defined as number of consecutive days. So let's say when 4 days in a row exceed a temperature of 33 degrees Celsius. Okay. And I can even make that if I wanted, like 33.5. I can be very specific if I wanted to there. We then choose a time frame that we want to run this analysis over. So we could just do the whole thing. And I enter in my email address here. Do this little and boom, hit the button. Did it go? You know what? Sometimes when I'm on the VPN, it doesn't always work. It will work on your end, trust me. And I think it may have worked, or I may have hit a wrong button. Doesn't matter. The whole point is about 10-15 minutes later, I'll get an email with the data that I just requested for this specific grid cell, for those years, for this specific customized variable for number of heat waves. And I'll get my own data that I can use in my analysis. It's an enormously powerful way to browse these data. And it's something that previously would have required some pretty advanced coding skills and definitely a very big hard drive to host the 40-odd terabytes of data that it takes to run this website. So that is the analysis page. Now, for the transportation sector, there are many critical thresholds out there. So for just a few examples here. So in city of Winnipeg, there was a day where the temperature got above 36.5 degrees Celsius. And at that point, there was a lot of issues with concrete heaving and cracking and whatnot. Similarly, it was found, a study found that a number of days when there was 10 millimeters or more precipitation, road safety issues increased dramatically. Another case study out of Ontario from Metrolinx discovered that days above 37.7 degrees Celsius resulted in issues where they had warping of rails, they had to slow their trains down and that sort of thing. So there's a whole bunch of critical thresholds out there that apply to the transportation sector. And you can use this analysis page to run these yourself on your own desktop computer, which is really, really cool. Okay, one last thing here from ClimateData.ca. We have the I won't bother doing a live demo for this one, but there's a download page, and this allows you to download full data sets as well. So the analysis page allows you to query those data sets to find values that are interesting for you. Or if you want just the full data set, you can download that as well. Okay, so just really quickly before we close off this first section here is how are CMIP 6 data different than CMIP 5? Okay. Well, CMIP6 has an increased spatial resolution. And this allows those models to represent processes such as clouds and water vapor aerosols in more detail than ever before. And as a result, it has been found that the CMIP6 dataset is a little bit more realistically recreates extreme precipitation events. Okay. One interesting, should we call it, side effect of this increase in spatial resolution is that some of the models running the CMIP6 dataset have they have higher climate sensitivities than CMIP5. Climate sensitivity meaning that for the same, say if you double the amount of CO2 in the air, the CMIP6 models will report back a higher change in temperature than their CMIP5 counterparts did. So higher climate sensitivity. It's not necessarily wrong, but it's just an interesting result. And it's a bit of an active conversation right now in the climate research community, which is, okay, that's interesting. We need to look into this further. Why are the CMIP6 models somewhat more sensitive to climate forcings than CMIP5? So related to that very much is the question, do you have to redo your work now that CMIP6 is out? And the unfortunate, there's not a black and white yes or no, but it's a sort of it depends type answer. So like I said, no, sorry, not like I said, but CMIP6 model results exhibit many similarities to CMIP5. If you're zoomed out to the Canada level, and I give you a map of CMIP6 data and a map of CMIP5 data and tell you to figure out which one is which, you won't be able to. They'll look identical, okay? And so CMIP5 data is still valid. There's nothing wrong with using that data. It is, though, and this is sort of our official recommendation here, it is recommended that you use CMIP6 for all new work requiring future climate projections, and that you examine the CMIP6 data to see how similar or how different it is for your location before making the judgment call, your own personal judgment call on whether you should redo your work using the new data. Okay. And if you want to learn more about this, because I would really appreciate that, you must have lots of questions about this and more questions about the climate sensitivity and that sort of thing, please do visit the website and specifically our learning zone, where we have published a whole bunch of new articles pertaining to CMIP6. Okay, we've done the first part of our outline, and I've nattered on for a good half an hour already. The next few parts are a little bit shorter, don't worry. Okay, so let's get into global warming levels. And as I mentioned at the beginning, global warming levels are another way to look at future climate scenarios. So let's remind ourselves of what we've already seen. When we go to ClimateData.ca, we zoom in on the map, we click on the data, we get this time series chart, which demonstrates how our variable changes over time under various SSP scenarios. Now, for those of you who have done this already, you've used climate data, you've tried to integrate it into your work and develop policies and other various solutions for reducing your climate risk, you've probably had one or more of these common questions crop up. So first of all, the range of values between scenarios is very large. Should I plan for the whole range, right? You look here, it's like, this is the current sort of range of our climate system. We have some cold years, we have some hot years, or if this was precipitation, some dry years, some wet years. There is some variability that we have to account for, some uncertainty in what any particular year will be. When we look at the end of the century, this range is absolutely ginormous and is a whole other can of worms to try to understand how to deal with those various, that type of range. So should I use the whole range? Are some scenarios more or less likely to occur than others? Well, as we previously discussed, not really. We can't really ascribe a likelihood to these various scenarios occurring or not occurring. Certainly out there, a lot of folks like to say, well, SSP5, this high carbon scenario in red, it's probably pretty unlikely, right? You know, this would require a lot of effort on humanity's part to change the climate of the world. We're not even sure that that's physically possible. And similarly, SSP1, the blue line, I mean, let's face it, we missed our exit off the freeway, right? We have passed that point in time. And so we can probably safely ignore the blue scenario as well. So why don't we just focus on the green line? And while that might seem like sound logic, it's not always so simple, because there's a big difference between the scenarios which describe the emission of greenhouse gases into the atmosphere and the climate models which talk about the concentration of greenhouse gases in the atmosphere. And there's a big difference there. Emissions are one factor, but then through various feedback processes, through various unknown parameters in the climate system, like, well, what's going to happen to deep ocean cycling of carbon over 100 years, and that sort of thing. It's really hard to rule out for sure that the climate won't get up somewhere into the red zone. Okay, and likewise, for the same reasons, we can't rule out necessarily the SSP1 scenario. There's too many uncertainties, and those uncertainties also relate to future technologies and that sort of thing. So are some scenarios more or less likely to occur than others? Not really. It's a really hard thing to provide guidance on. What scenario then should I use for my work? Well, you won't find an answer from someone like me. It's too difficult to tell. I'll just kind of give a shrug. Well, I don't know. And what happens after 2100, right? When we look at this plot, I mean, it ends at 2100, but these lines have a trajectory. They're definitely going to continue on that path beyond the end of the century. And for a lot of our long-lived assets that we're designing and implementing right now, things like buildings, for example, they are expected to last beyond the end of the century. So these questions are wonderful questions, but they don't necessarily have standard answers, and they're going to depend on many factors, including personal risk level tolerance, more detailed analysis, time frames. If you're looking at something that is an asset that's designed to last 25 years versus 200 years, and so on. But going back to this graph, for those of you who have used this climate data before, you may have also noticed something kind of interesting. Like, okay, let's say, for example, this is the threshold that you care about. 40 degrees Celsius is the point at which impacts or disruption or damage starts to occur to your particular transportation asset. Under the SSP5 scenario, the red line, we hit that threshold. We first hit that threshold pretty early, around 2055 on this graph. But if we follow the SSP2 scenario, the middle of the road scenario, we hit that later, but we still get there around 2080s or so. And so we have to think a little bit here of this isn't necessarily an if question, more it's a when question. For temperature dependent processes, the impacts scale based on the magnitude of the warming and not often not the pathway of that warming. In other words, what I mean here is that it doesn't matter how quickly or how slowly you get to that threshold value, the impact that you will have to deal with, that you'll have to accommodate in your system, is pretty much the same. That's illustrated by this graph, which overlays the older RCP 4.5 and 8.5 scenarios. This is SSP2 and SSP5 for our purposes here. You can see that the change in the hottest day of the year on the y-axis is dependent on the change in the global temperature, okay, and not the pathway that you got to that particular global warming level. Okay. Importantly, warming, as we said, continues in most scenarios beyond 2100. And so even in the fairly low carbon scenarios, we can still get eventually to quite high global warming levels. It just might take longer to get there. And so what do we mean by level of global warming? Well, simply it's presenting the climate changes according to the global average temperature and not a specific scenario. This has many advantages that we'll see in a second. But first, a question. How much future global warming might we expect to occur in the future? This is an interesting question, and it's slightly different, subtly different from asking the question of which scenario is most likely to occur or not to occur, because we can start to do a little bit of forecasting in answering this question. Let's look at a few examples here. Okay, so first of all, how much global warming has happened to date? So the global temperature has increased approximately 1.1 degrees Celsius over the past 120 years. By the way, Canada, being a northern nation, is sensitive to these global climate changes. And Canada has warmed at roughly 2 times this global rate and 3 times this global rate in the north. And this warming is not symmetric all year round, but rather we see our winters are warming much faster than our summers and the other seasons. Okay, but all that's a bit of an aside. So global temperature has increased 1.1 degrees Celsius over the past 120 years. So how much global warming should we expect to occur over the next short term? Well, here's a couple snippets from a few recent publications. I'll just read them here. So this first one from the IPCC report published 2 years ago said that human activities have estimated to cause approximately 1 degree Celsius of global warming. So I said 1.1 in the previous slide, and that's because this is 2 years out of date. So one degree of global warming above pre-industrial levels. Global warming is likely to reach 1.5 degrees Celsius between 2030 and 2052 if it continues to increase at the current rate. And here they give that sort of high confidence statement. This means that there's actually some statistics behind this statement. The IPCC is basically saying, look, there's a 95% chance that we're going to reach 1.5 degrees of global warming over the next few decades. Okay. By the way, when we say reach a global warming level of 1.5, we mean like permanently exceed it, like not just 1 year hits 1.5 and then it goes back down and then, but rather we've reached and exceeded 1.5 degrees of global warming. So the World Meteorological Organization in May of 2022 said that the chance of temporarily reaching 1.5 degrees Celsius has risen steadily since 2015 when it was close to 0. So for the years between 2017 and 2021, there was only a 10% chance of exceeding 1.5. That probability has increased to nearly 50% for the time period we are in right now. So we would expect to reach 1.5 degrees of global warming any year now. Okay, likewise, the UN publishes an annual report on the emissions gap. So looking at global emissions and how far our current emissions are from our target set at the 2015 Paris Agreement. Okay, so the nations of the world came together and said, we agree to limit global warming below 2 degrees Celsius, and ideally we want to get it at or below 1.5 degrees of global warming. That's what we agreed to. Okay, and so every year, though, we have not been on track to meet that target. Emissions have continued to increase. So there's a widening emissions gap, and the UN reports on this every year. So if we take last year's annual report, you can see that they have this really interesting graph looking at the likelihood of reaching various global warming levels based under different scenarios. So if we look at the current policies scenario, there's a 50% chance that global warming will reach or exceed 2.6 degrees Celsius by the end of this century. Okay. If, however, we reach our Paris targets, so the nations of the world reach what they promised back in 2015, then we will limit global warming, or there's a 50% chance we'll limit global warming below 2.4 degrees Celsius, which is higher than 2 degrees Celsius, importantly, right? So in other words, even if we reach our goals, there's a strong likelihood that we still surpass the tipping point, the 2 degrees Celsius value that we were trying to limit global warming to. And in fact, even under the most optimistic scenario, one where we reach our goals and then we go much further to reach the voluntary net zero targets that were set, even then global warming levels are still above 1.5 degrees Celsius and are awfully close to the 2 degrees Celsius threshold. To visualize this a little bit different, you can see how the various scenarios evolve over time. And even the most optimistic scenario done in purple here still jumps above the 2015 Paris target of 1.5 degrees Celsius. And most scenarios blow past the 2 degrees Celsius tipping point. So why does this all matter? Why are we talking about global warming levels at all? Well, it's because, as I said, impacts scale to the magnitude of global warming and not the pathway. And this is really powerful and really apparent when we look at some recent climate attribution studies, which have looked at some of the quite severe extreme weather events that have occurred in the past few years. So if we take the 2021 British Columbia atmospheric river event, that flooding was determined to be 2 to 4 times more likely as a result of the human-caused climate change that has occurred to date. And importantly, in a future of 3 degrees of warming, these sort of events might be expected to roughly double in their occurrence. So we can really clearly see how using a global warming level allows us to really leverage what it is these climate attribution studies are telling us, which is that if we get to this level of warming, we will expect these sort of events to occur much, much more frequently. Another example, also out of BC and the Pacific Northwest, also out of 2021. 2021 was a bad year for BC. Here is where we saw those extreme temperatures occurring, 49.6 degrees Celsius in Lytton, BC, and the huge devastating fire that followed those events. So this heat wave event was approximately a 1 in 1,000 year event, an extremely unlikely event to occur, very rare. But in a world of 2 degrees of global warming, such an event might occur every 5 to 10 years, according to this study. And so even accounting for uncertainties and unresolved things that are still being researched, even taking an extremely conservative approach to these values, you can really see how how impacts scale quite dramatically with global warming levels, and how important it is to keep those global warming levels in check. I'm going to skip over this slide here. So that is section 2, global warming levels. We're now seeing why we're using these global warming levels more and more out there in the wild. It's because they really nicely communicate the link between impacts and climate change. And it's really nice to get away from scenarios, which, as we saw, have lots of questions associated with them. Which one is most likely to occur? Which one should I follow? Instead, let's just focus on global warming levels, which, in that case, you're not really concerned with which scenario do I follow, but more concerned with how much time do I have And that will depend on the asset that you're responsible for. Okay, let's move on to chapter 3 here, which is this new tool called the Design Value Explorer. And you're going to see exactly why we've been talking about global warming levels for the past 20 minutes. So the Design Value Explorer is another brand new thing. It was launched publicly just this past February. And so it features 19 climate design values, and we'll explain what those are in just a second. It allows you to browse historical values as well as future projections. For the first time, we can look at future projections of the climate design values that we care about. This was a big undertaking and a huge partnership between Infrastructure Canada, Natural Resources Canada, Environment and Climate Change Canada, and the Pacific Climate Impacts Consortium. So what are climate design values? Well, these are the values referenced within code, specifically the building code and the highway bridge design code. So they include values like the 97.5 percentile of the maximum July temperature, a very specific value that is used for all sorts of applications, like determining the amount of active cooling your building might need, the level of insulation it might require, and that sort of thing. But also things like relative humidity, horizontal driving wind pressure, wet bulb temperatures, and a whole sort of other things, which are, as we previously, when we were looking at ClimateData.ca, those variables are not available. On Climate Data, we just have temperature and precipitation-based variables. So this is a very exciting tool because it's for the first time allowing folks to look at the variables that they really care about across Canada. So let's go for a little live demo of this as well. And there's, sorry, my share thing is in the way. There we go. Okay, so here I am on the Pacific Climate Impacts Consortium's website. That is pacificclimate.org. And if I go under the analysis tools, I can see first up, we have the Design Value Explorer. So I'm going to proceed to the Design Value Explorer. Now, this application is pretty resource intensive and similarly operates a bit slowly. So if I'm not able to get it to load for us here today live, I've got some backup slides, but oh, it looks like it's going to go. We'll just give this a second here. And don't worry, I will finish on time, despite the fact that it seems like I might not. The last section is going to take just a few minutes to go through. So we can browse a number of different climate design values. So for example, here I've got the annual maximum snow load 1 in 50 event, which is, again, as mentioned, the exact parameter listed in the model building code of Canada. So that's a value that for engineers makes a lot of sense, and it's what they're looking for. I'm allowed to browse these changes under various global warming levels. So that's why we spent so much time going through these in the previous slides. So I can look at, for example, 2 degrees Celsius. We saw that 2 degrees Celsius was a level of global warming associated with a huge increase in those kind of heat wave type events that BC experienced in 2021. So we can choose the level of global warming that matters to us based on the types of impacts that we want to account for. You can then click on this map so you can get these values here. These values are spatially interpolated. So you're not restricted to only the weather stations that the building code references, but rather you can go anywhere across the whole country. And you can look at how these various design values evolve over time under various global warming scenarios. So it's an enormously powerful tool. That's the Climate Data Explorer. Sorry, the Design Value Explorer. So just quickly, what makes this data so innovative? Well, it utilizes the Canadian regional climate model, which is what's necessary to do the sub-hourly modeling of the processes like driving horizontal wind pressure, ice accretion, permafrost degradation, and that sort of thing. Okay, so it uses this new model. Now, this is really, really powerful and really cool. What's the trade-off? Why does ClimateData.ca still use statistical downscaling if we can now do regional climate modeling for the whole country? Well, very plainly, it's because it's still enormously computationally expensive to run these models. And so this is just one regional climate model. It is run many, many times to create an ensemble of values, but it's just one model. So ClimateData.ca has 26 models. And it's really nice to have many different types of models. They are developed, right, by independent research organizations from around the world. So having 26 models increases our confidence in all sorts of things. This is one climate model. So you have to know that going in. But the benefits, that being the incredible fine scale, both temporal and spatial scale of this data, is really cool and really powerful. So we've already looked at that. All right, so that's the Design Value Explorer. I think for folks responsible for any type of physical infrastructure in Canada, you're definitely going to want to go and check that tool out. And now that you understand global warming levels, hopefully it's going to be easier than ever to dive into that data to get what you need. So just really quickly to wrap up here, what's coming next? We have a lot of new things coming out this year. Okay, one thing that was actually just announced was future IDF data. So these are, if you go to ClimateData.ca right now, you'll be able to browse IDF intensity, duration, frequency of short duration rainfall events. You can look at how those are expected to evolve over time using an innovative temperature scaling technique. So it's a whole other ball game right there. A whole other hour could be spent just talking about that, but that's live. You can go to the site, check that out. We also have new fire weather index data that's expected to come online over the next year. Buildings, climate zones, Humidex, very powerful, especially for folks in the health sector, but applies to everything because we take humidity and see how that magnifies the apparent temperature, which is really, when we think about human systems, that's what we care about most, is the apparent temperature. We've got lots more content coming to our learning zone, more sector modules, new data extraction tools, and on and on and on. So we're working on some really cool applications. Like this is an application, it's still in its draft format here, but it shows how fire weather index values are expected to change over time. Really important, of course, because fire is one of those impacts that's expected to only increase in frequency and severity as the climate warms. Looking at how buildings climate zones are expected to evolve over time. These are the zones referenced in the in code, and determine things like, you know, level of insulation required for your structure and that sort of thing. So we're working on a data product there to demonstrate those. Humidex, so looking at various thresholds like the Humidex above 30, 35, 40, 45, and that sort of thing, looking at how annuals and seasonal values are expected to change over time. So expect to see that hopefully by the end of this month. That might be a little ambitious, but very soon expect to see that launched. And like I said, so much more. To make sure that you stay up to date on everything and that you don't miss out on future updates, we have a lot of really cool outreach resources available. So we have a blog on ClimateData.ca/news, where we post about everything that's coming up We have a newsletter, and again, it's linked here, but you can go and subscribe. You can also go to ClimateData.ca and see the sign up form on the homepage. And we've got some social media accounts as well. So please do take the time to find us on social media, to follow us, and that way you'll stay up to date on everything we're putting out. So again, if you want any further clarification on anything you've learned today, if you want to get in touch with us to talk about CMIP6 data or anything else, drop us a line. Our email address is ccsc-cccs@ec.gc.ca. It's a lot of C's. And thank you so much for your time. And we have time now, as I understand it, for some questions. So back to you, Laura.
Yeah, thank you so much. That was a great presentation, super informative, and a lot of new information for me too. So that was super great. We do have a few questions in the Q&A box, so we'll get started with those. If people have other questions, go ahead and put those in now. So first question, does CCCS have plans or have partnerships to implement more weather stations across Canada? Climate model ensembles are great for regional scale analysis, but often not good enough to apply at local scale.
Yeah, great question. So no, the Canadian Centre for Climate Services is not responsible for weather stations across Canada. So all of that is housed under the Meteorological Service of Canada. And while I appreciate that we're all part of Environment and Climate Change Canada, really we're quite siloed in that way. So the CCCS doesn't have any say, or therefore doesn't have any plans to implement new weather stations. But 100% sympathize with you. There's a lot of areas of the country where we have huge gaps in our climate data. And it's something that I hope would improve over time. So sorry, I don't have a great answer for you.
Question 2, which SSP are we following currently? Is it SSP2?
So that's a great question. I mean, if you were to look again at that one of those time series plots, all of the SSPs are kind of all jammed together until about 2050, they really start to diverge and you can sort of tell them apart. We're kind of following all the scenarios right now. From what I've been sort of told and from what I can tell from the literature, we're on track for SSP, was it SSP4? No, SSP, okay. I can only remember it in the RCPs, RCP6, which I think translate to SSP4, or maybe that's SSP3. One of the ones that we don't include on ClimateData.ca because it's not one of the ones typically included in the model. So for the modeling organizations out there, they're told to prioritize which SSPs to run. So make sure you do SSP5, make sure you do SSP1, make sure you do SSP2. If you have time, do number 3 and number 4. And so not all modeling organizations end up doing those. So I think which one are we on is a bit of an unknown at this point. Somewhere between SSP2 and SSP5 is what I would suggest is an okay answer. Yeah.
Okay. Is the CMIP6 BCCAQ data on a per model basis? It's not an ensemble of all models. One must select an individual model there. If one is interested in an ensemble, that's up to the user, correct?
No, so yeah, when you go to ClimateData.ca, you're browsing an ensemble of 26 climate models. So that's when you look at the range. I guess I could share my screen just really quickly again here, but there we go. Just to make the point clear here. No, I didn't do it. Share screen. There we go. So just there we go. So when you look at like you've got this range between the very top, I don't know, trying to find a clear example. Oh, you just take the gray range here. I mean, you have the black line, and that represents the average, or the median specifically, of a 26 model ensemble. And then the top and the bottom are the 90th and the 10th percentiles of that ensemble. So you get the ensemble of those 26 models when you go to the website. If you require the individual model projections, we're working to better supply that information to users. It's presently not available through ClimateData.ca, but it is available through other partner organizations, or sometimes we run custom extractions for folks who have specific applications. So we can get you the individual model results if needed. Everything you get on ClimateData.ca is an ensemble, though. So I hope that answers your question.
Great, thank you. Next question. Are you planning to include return periods, for example, 10 years? This information is very useful for climate risk assessment methods like the PIVC and ISO 14091. And maybe you can mention what a return period is for, for those who may not know.
Yeah, for sure. I mean, yeah, return periods are super powerful. We looked at a few, right? Like, you know, historically, the BC heat dome event was found to be a 1 in 1,000 year event, which means on average, you might expect that event to occur once every 1,000 years. I mean, that doesn't preclude having 2 in a row. It just means that it's less likely for to have those all stacked up together. It's a very rare event. No, unfortunately, we don't have active plans. I mean, it's something, believe me, we've chatted about it. There's a lot of factors to consider. Everyone wants to do it. It's just going to be a matter of finding the time and to do some research to develop those new data sets. So we really hope. Yeah, stay tuned for more on that.
Great, thank you. So can you please explain more about the IDF-CF? How do you read the data for IDF, and could you provide an example?
Sorry, how do I rate or how do I read?
Read the data.
Oh, yeah, okay, sure, yeah. So I'm going to share my screen again. So, okay, so you can see that, yeah, okay, cool. So if we go to ClimateData.ca, you click variable, and right in the quick menu here is the short duration rainfall IDF data. You have to get past the splash screen, which sort of explains a little bit more about the procedure that's used to create these data. They are station-based data. So if you click on a station, you can access the historical values, the scaled values under CMIP 5 and CMIP 6, and then a what's called quick start CMIP 6 package here. And this is really just it's designed to be a little bit easier to use if you've never extracted this data before. It includes a README file, which has some important sort of documentation about how to read these values. In terms of what they actually look like, we have, if I go to the news page here, so this is our blog page. And again, I really encourage folks to come here. You can sign up for our newsletter. If I go, let's see, new and noteworthy. Oh, here it is. So the new climate change scaled IDF data. So this goes into the technique again. It tells you exactly how to access this data, like I just showed. And then it demonstrates, so once you load this data into like a spreadsheet like Microsoft Excel, this is what you get. And it demonstrates how you can use, and I suppose actually this is where return periods come in. So I guess it was wrong to say we don't have anything to do with return periods. IDF data includes the return period. So we have the 1 in 100 year precipitation event. If we wanted to know what the 1 in 100 year 1 hour rainfall intensity value is, then we would just go between that row and that column and get, in this case, it's 34. So that's 34 millimeters per hour. That's the intensity of rainfall that we would expect to occur for this particular example location once every 100 years. And then you can look under various scenarios like, okay, well, how does that change under SSP 5? There's a whole other spreadsheet file that you load in and you do the same process. The new 1 and 100 year value might go up, or it might stay the same. I don't know. It sort of depends on where you are. And then you can look at how that changes over time. And maybe that 34, you know, that becomes more like the 1 in 50 year event, or maybe 1 in every 25 year event, and that sort of thing. So that's how to get the data, and that's how to read it. And again, this, you know, what I can do is put this right in the chat, right? Chat to everyone. Yeah, check that out, and hopefully that answers your question. And if not, please get in contact with me.
Yeah, they just put a clarification as well in the Q&A box about the future change factor IDF from the
okay.
Design Value Explorer. If that.
So you're wondering, so if you look at like this, the IDF CF value and how that changes over time.
Yep.
You know what? So okay, so to be honest, this is it's displayed as a ratio, and what that is it's basically a multiplication factor. So that is the future value compared to or divided by the baseline value. So for, you know, like here at the end of the row here, 1.452, you would take the short duration rainfall event and you would multiply by that factor to understand what the future value is. I might suggest that you actually reach out to PCIC, or the Pacific Climate Impacts Consortium, for more detail on exactly how that was calculated and how to apply that. Because I'll be honest, I don't know the specifics. But by the way, that contact information is easy enough to find here on PCIC's site. Well, somewhere I'm sure you'll be able to find. Oh, just hit contact. There you go, right at the very top. They're the authors of this tool, and they'll be the ones best suited to answer that question.
Perfect, thank you. Someone's asking, are the old RCP that they used last December, January still valid? Would you suggest that they rerun the variables with the new scenario SSPs? And they've also noted they're confused between SSP and CMIP.
Okay, yeah, so well, I'm gonna share my screen one more. Maybe I'll just keep sharing my screen. I don't need to stop. Okay, that's a really good question. Okay, so this is in the way. There we go. So if you go to ClimateData.ca, you go to Learn. That's what we call the learning zone. And here we have a bunch of articles detailing CMIP 6, the SSPs, and lots of questions like, should I redo my work, you know, using this new data? So it's going to scroll down. Here we go. Understanding future projections. So first of all, we've got the CMIP 6 frequently asked questions article here. This has lots of great, let's see, differences between CMIP 5 and CMIP 6. So for example, are there major differences? What is this whole climate sensitive thing and why does it matter? Oh, here, does the release of CMIP 6 data mean that the work I completed using CMIP 5 data is obsolete and will need to be redone? So this goes into that question. I sort of answered this briefly in the presentation, but there's a little bit more of a detailed reply to that right here. The answer again is it depends. It depends on the level of detail that you're looking at, both a spatial and temporal scale. As mentioned, CMIP 6 tends to capture extreme precipitation events a little bit better than CMIP 5. That's where I think most of the improvement is seen in that data. Temperatures, they kind of stay the same. until you look way off at the end of the century, where some of those higher climate sensitivity models begin to shine through. But overall, the averages, the overall picture, it's pretty much the exact same. So it's going to depend on the sort of fidelity of data that you're looking for, the level of detail that you're looking for your case study. And I'd be happy to chat more at some point about that if you like. But again, I'll throw this link into the chat. But then, okay, the second part of the question was confusion regarding CMIP 6. Can you reread that one?
Yeah, confusion between the SSPs versus CMIP. So
yeah.
I guess, yeah, where they come from.
Right. So CMIP is just, it allows for the world, like we get 26 climate models, and those are they're developed independently by research organizations across the whole world. And we need a way to make sure that we can actually compare the results of all of those models. So there's a standardized set of experiments that are suggested that all the international modelers perform. That's CMIP. CMIP is a way to allow the various independent researchers to communicate with one another. The SSPs, those are the scenarios that the climate models are running. So those are the, like the sustainability scenario, the middle of the road scenario, the fossil fueled development scenario. So those are developed by economists and demographers. What's the wrong word? Demographers. I don't know. Yeah, people who have a good understanding of how will population change over time, how will education levels change over time, and that sort of thing. So that's a whole sort of independent process, developing those scenarios, developing the narratives, feeding those scenarios into, they're called IAMs, assessment models, integrated assessment models, which take those narratives and develop the climate, greenhouse gas concentrations that then the climate models need to run. So there's a whole lot of sort of independent work that's being done, and it's all being sort of coordinated by the CMIP body. Hopefully that helps a little bit. Let's see, do we have, we certainly have a whole article here on understanding more about these shared socioeconomic pathways, which might go into a little more detail and help you understand them. But I don't have a good article here about CMIP, except for, I guess you'd probably find the answers in this frequently asked questions thing. So I'm going to just throw these into the chat here as well.
Perfect, thank you. Okay, are you planning to include information about ongoing changes based on observational data, for example, trend analysis? I think this is a very important point of departure to assess changes and validate the climate scenarios. In some cases, there are disagreements between observations and future scenarios in terms of sign of change.
Well, yes. Okay, so that's a really great question. Thank you for that. So you would expect, okay, so here's the thing, like climate models, they come at a very coarse resolution, 100 kilometers by 100 kilometer grid boxes. Within that 100 kilometer by 100 kilometer grid box, you would expect, in fact, it is 100% certain that you will find some location within that giant grid box where the local temperature is doing the exact opposite of what the climate model is telling you should expect for that region. And that is not in any way to suggest that the climate model is doing a bad job. It's just exactly what you expect when looking at climate. Climate is best understood when you zoom out and you look at the broad picture, 30-year averages over a large area. Because within that area and within that 30-year time period, you will find all sorts of trends that are seemingly going all over the place. These are actually not trends. That's the long and short of it. Trends, in order for it to be a trend, it has to be a statistically significant trend, which means you have to have a large amount of data that is going to demonstrate that this is not just sort of random chance or a result of the variability of the climate that you are seeing this maybe short-term decrease in temperature when the climate models suggest that temperature is increasing. All that being said, this is so it's one thing for temperature. It's a whole other thing for precipitation. Precipitation is even more difficult to model and suffers from even more variability. And we start to see the impact of teleconnections like, the PDO, the Pacific Decadal Oscillation, or the AMO, the Atlantic Multi-Decadal Oscillation. Oh, I'm kind of forgetting my acronyms a little bit today. But anyways, you have atmospheric processes that can create 10-year, 20-year cycles, natural cycles in our precipitation regime. And those come through in the weather station observations. And it doesn't negate that the climate model is saying, well, for this region, we expect an increase in precipitation. If the last 20 years are showcasing a decrease, that could very well be attributed to the broad array of variability processes that govern our climate. So all that being said, you should not, if you have weather station data and you perform a trend analysis and you get a result that is different from what the climate models say, you should expect that. That is, as a colleague of mine would say, a feature and not a bug. It is a certainty that the weather station is not going to agree perfectly with the climate model. But that it's like hard to wrap your brain around it, right? But it's like it's not that the climate model is wrong. It's that the weather stations are going to be manipulated by the incredible number of factors that can control how things like temperature and precipitation, how that evolves over decade-long timescales. So that being said, you can get historical data on ClimateData.ca. We provide the adjusted and homogenized climate data archive, which is a very nice and clean temperature and precipitation data set. So you can access all of that. You can download the raw weather station files. We have all of that. And then you can perform your own trend analyses on that data. So that is most certainly a large part of our website. And I guess I can just quickly show you where to get that here. It's the ClimateData.ca/download. And here, yeah, station data. You can also access IDF curves, by the way, through this interface. And AHCCD, that's the adjusted and homogenized Canadian climate data set. Hopefully that's, I imagine you might have more questions, and that would be very healthy if you did. So we should set up a time to chat if you want to learn more about that. Thank you.
Perfect, thank you. Okay, we just have a couple of minutes left and one question left, so maybe we can get to that one quickly and then we can wrap up. So last question, do the IDF values from ClimateData.ca and another tool called the IDF CC tool 6.0, which is developed by Western University, come from the same data set?
So no. So the IDF CC tool from Western University uses a very different approach to develop future-facing IDF curves. It is not. I'll say. I think this is probably the fairest answer I can give. It's so the Western University's tool does not use the method that has been adopted by Environment and Climate Change Canada and the Canadian Standards Association as being the sort of accepted technique for looking at future IDF values. I think from my very limited understanding of the Western tool, it uses some very powerful statistics and it looks really promising. I think the limitation is the information that's fed into those models. So typically a model is if it's like garbage in, garbage out is the mantra, right? So if you don't have clean data going into the process, it's hard to trust the data that comes out of it, regardless of the rigor and regardless of the theory that is driving the model. So from my understanding is that the tools, they're very different in their approaches. They produce different values. And the one that has been endorsed by Environment and Climate Change Canada is the one on ClimateData here. And I'll point you to some resources as well on this, because it comes up in a lot of the presentations we give, because it's a great question. Like, well, which tool, which data should I use? Which one should I trust? Which one is good versus bad, right? And so if we look at, if you click here to the IDF section here, topic number 6, there is, I think it's this first article here, which goes into what the method is, how it has been adopted by the Canadian Standards Association. It explains how it is, why Environment Canada has chosen this technique. And then it runs through a few examples on how it works, essentially. It's a very simple, I think simple is the right term, technique, a technique that accounts for the scaling of extreme precipitation based on temperature change. Temperature change is something that we have a lot more confidence in when it comes to our model outputs than precipitation change. Temperature change is also a key factor in determining the amount of water vapor the atmosphere can hold in the first place. So there is a relationship, a strong relationship between temperature and the degree of extreme precipitation that is possible for a location. So this takes advantage of that strong relationship called a Clausius-Clapeyron relationship, which, and that's how these data were produced. So I know that probably doesn't answer your question, but unfortunately, that's kind of the best I can do.
No, thank you. That is all our questions. So I think I'll just wrap up by saying, first of all, thank you so much, Ryan, for your presentation and for sticking around to answer everyone's questions. It's great that we got to everything. In the chat, people will find a link to a post-webinar survey that we would greatly appreciate your feedback on how we can continue to improve our webinars. Transport Canada doesn't currently have any upcoming webinars, but if you want to keep updated, I've put our email address in the chat and you can send us an email to be added to our mailing list. And then before we sign off for today, Ryan, just any closing thoughts before we go?
No, thank you so much. Like I said, it's wonderful to really nerd out on some of this stuff, and it's great to see such great attendance and so many great questions. So thank you. And please, if you sign up for our newsletter, that would be fantastic. You can really tell I'm pushing that. I really want to get, but we want to make sure the information we're producing is getting out there. So so thanks again, everyone, and enjoy the rest of your day.
Perfect. Thank you. Thanks everyone for attending. Have a great rest of your day.